Okay, so this is the second redox video, and I'm just going to pick back up from the first one. Now, I mentioned in the earlier one that oxygen is a common oxidizing agent, and that's why we chose that term actually. But there are many other very common compounds as well as ions that act as oxidizing agents. And I'm going to draw a couple of others here just to kind of show them in action. And just for the moment, I'm going to erase our good old zinc, but I'll come back to zinc in a minute. So another very common oxidizing agent, and we talk about this in, oh, and by the way, I'm going to quickly say a tie-in to life sciences is obviously oxidants and antioxidants are very important compounds, chemicals in the biosciences, and I'll make a tie-in to that when I get to the end when I talk about organics. There are many oxidizing agents that are even common. So bleach is one, your household bleach is one, which is essentially a chlorine-based compound that just happens to be in a situation where it wants to pull in more electrons. Okay, so before I go to bleach, I'm going to cover one that's even more common than bleach, which is chlorine gas. So chlorine gas is a diatomic gas, very similar to what oxygen is. It's a diatomic gas. And when you when you react chlorine gas with hydrogen gas, the chlorine acts as an oxidizing agent, meaning it wants electrons. And it would react with hydrogen, and hydrogen is kind of like the classic reducing agent because it's happy to give up electrons. And hydrogen, when mixed with chlorine gas, I should probably write these as both gases, reacts to form two hydrogen chloride gas molecules. Okay, both of the reactions that I'm showing here, the burning of hydrogen and the reaction of hydrogen and chlorine gas, are very exothermic, meaning they both give off quite a bit of heat. Essentially meaning that both of these compounds that are reacting are happy to be involved in this redox reaction, happy from an energy standpoint. The hydrogens, in the case of the top reaction, when hydrogen mixes with oxygen, the oxygen atoms get what they want. They want two extra electrons, which makes them, from an energy standpoint, more stable at lower energy. And the hydrogen gas gives up the electrons, which actually allows them to achieve a lower energy state as well, as basically hydrogens that are covalently bonded to oxygen. Same sort of thing happens with respect to the second reaction that I'm showing here, is that chlorine, in this reaction, the chlorine gas molecule turns into essentially a chloride ion. And again, HCl, when you look at HCl, it is, chlorine starts with 7 electrons. If you look at chlorine in the periodic table, it's 1 away from completing that row, and completing that row is 8 electrons total. So it has 7 to start with. But when it reacts with hydrogen this way, it picks up, maybe these days I'll get some other colors, it picks up an extra electron here from the hydrogen. And the hydrogen is hanging out here, essentially bonded to the chlorine, but it's given up its electron. Now again, it's sharing it, technically speaking. The hydrogen atom is sharing these 2 electrons with chlorine, but the truth is that it's barely, the electrons have shifted dramatically towards the chlorine side, because chlorine is much happier when it has all 8 of them surrounding its nucleus. So this is what HCl looks like, and of course, since they're diatomic, we end up with just 2 of these. Okay. All right. Now, again, I kind of refer to this as happening as energy downhill, meaning both of these reactants end up in a more stable, lower energy state than what they started with. Okay. Now, chlorine's important, and we'll come back to that. Now I'm going to bring my zinc back up. Okay. So again, my zinc, got a pen all over me. My zinc reaction with zinc plus oxygen results in zinc oxide. Okay, and similarly here, the zinc is kind of in the +2 state. It's given up its 2 electrons. The oxygen has gained the electrons the way did I draw this right? Yeah, I didn't draw this right, dummy. Okay, good. I'm glad I corrected it now. It's not ZNO2. It's two of these and two of these. Okay, and we're going to get to another video is going to show why this is, and in fact, part of the challenge of redox reactions is properly balancing them. By the way, I drawn originally what wasn't in the earlier video was correct. This is actually correct now. So in this case, both oxygen atoms have picked up an extra pair of electrons. Each pair comes from a zinc atom. So a zinc atom gives up 2 electrons because it is the reducing agent and it is being oxidized by this. And each oxygen atom picks up 2 electrons, resulting in zinc oxide. And again, zinc oxide is a solid, but you can think of it as essentially a zinc cation and an oxygen anion being bonded together in a solid lattice. Okay. Right. Now, here's the big question, and one thing I meant to say is that zinc is actually happier, prefers to be in this +2 state than it does being actually in its elemental neutral state from an energy standpoint. And I've already made that same statement about oxygen. So that's why this happens readily. The big question then is that, well, how do you ever make zinc metal in the first place then? If zinc would rather be in a +2 state oxide, how do you make zinc metal? A good question, because all metals, almost all metals in nature, exist as ores, basically as rocks in the Earth's crust. And zinc is no exception to that. So zinc, we would actually mine for zinc, and we would find zinc ore, which is essentially zinc trapped in rocks, which is essentially it's zinc oxide, but it's kind of along with a whole bunch of other kind of rocks of ores like calcium oxide and potassium oxide and iron oxide and a bunch of other rocks like this. Okay, so how would you make zinc then? Well, it turns out you make zinc later by, if you were to dig up zinc oxide, you can actually react zinc oxide again, like in a furnace, with, let me actually draw it down here. You could take zinc oxide and roast it with chlorine gas, meaning mix it at high temperature with chlorine gas. And what you'd find is, and I'm not going to balance this properly, is that you'd end up, since this is an oxidizer, it can oxidize, I didn't do this right, did I? Okay, not the right reaction. Let me actually take a simpler one. I wonder if I should start this tape over. I don't want to. Just bear with me. So a way of making zinc, taking zinc oxide and making zinc, one way, kind of a real simple way, is to mix it with hydrogen gas. Okay, hydrogen gas is a reducing agent, and so what you'll find is that hydrogen gas, when reacting with zinc oxide, probably at high temperatures and maybe in the presence of a catalyst, will produce zinc metal and water. Okay, so from this standpoint, the hydrogen became more stable, along with acting as the covalently bonded to oxygen elements inside water, and kind of as a trade-off, the zinc actually changed its state. It actually picked up the 2 electrons that it likes to lose, picked them back up to form the neutrally charged zinc metal. Okay, so this can be done, but essentially, in order to actually go uphill from an energy standpoint, in the case of something like a zinc oxide, you have to add in a strong reducing agent. In this case, hydrogen. Okay. Okay. I think that's all I want to do with this one.